then the online student can hear us. Alright, so we've been talking about different things, including object-oriented concepts, right? The week 1 we talk about concepts 2. So 2 and 3 so far we were keep talking about those ADT stuff, right? Okay, so for today we will continue to talk about something about ADT modeling, this kind of thing, so that before we actually start our textbook stuff, you have enough background knowledge. Because I hear somebody email me said he or she doesn't even have a formal data structure course yet, but it's okay. If you have already taken that course, that's great. Okay, but if you haven't, it's okay. I'm here still let you review that a little bit, and from there we can generalize our concept of OO and get some mind of using OO to design. Okay, all right. Now last week we were talking about this examples, right? Stack, okay, dictionary example, stack example, and reference. So we're trying to use the idea of OO to design that, to see the refrigerator as an ADT, right? Remember that? I want to repeat that a little bit. Not this one. The ice dispenser. Is it in here? Oh yeah, that's the homework following that ice dispenser. Come on. Yes, if you remember this thing over here. I believe some of you have already forgot. Okay, so in terms of ADT, let's find what are the data here. Water. Yeah, right, water. And what are the functions? Ice cubes, right? Because they are doing something to the water, right? Like doing something to the data, change the status of the data, change maybe from water to different water or different status. Okay, how about the out of ice indicator?
It's not an operation.
It's like a
Boolean message.
It's like a Boolean.
Is it?
It's an operation.
Is it not? It's not doing anything to the.
So it will work as those get operation,
Yeah.
right? It returns a value. Okay, so if you think about the encapsulation, we don't want anything outside to touch the data. Okay, but sometimes we do want to get something about the data, then we use the functions. So those are like the interfaces between, So we cannot, from outside the world, we cannot do anything inside, but there's some interface there, right? Get cubes or get some status of the data. Yeah, we cannot do something. We don't want to do something directly to the data. Although I know maybe in some of the object-oriented programming language, you can set public, something like that. But well, actually, it works more like we should do. What we should do is use the method to get the data. Okay. Yeah, and the walls here, they work as the encapsulation. Okay, so this is pretty good example of object. Okay, to help you understand object. Yep. Okay, so today let's start another interesting stuff. It's still ADT, but let's go a little bit deep. Okay, more on ADT, and this time we will doing some maybe algorithm and implementation. Okay, more technique. Okay, so that you can have more fun, right? Okay, hopefully you can have more fun. All right. Okay, so we were talking about stack. We were talking about a dictionary, those things which exist in our real life. Okay, let's see something else. Maybe it exists and it's more abstract. Maybe if I want to get who is in my class, I need a list of the student's name, right? A list. So a list, and also yeah. So let's think about list. So what is the feature you think of a list? Think about a list of names, a list of something else, a list of courses, yeah, something like that. So what are the features there?
Typically, that's like the first item that you would start with.
Yeah. Let me ask you a question. Do you think a list does a list have order?
It's index based.
It can be either.
List.
A list is out.
It's in.
Yeah.
A linked list or just annual
It,
list?
it depends on whether.
I'm talking about a list in general.
List.
Well, always have an order. In the order you put it in doesn't mean that it's, sorted.
Yes. Yes. Right. So list does have a order, an order. Okay, you have the first elements in your list, second, third. Okay, like array has an order. Okay, and how about set? Do you think set has an order? More mathematically, think no.
Stack should be ordered because what you.
Stat? No, not stack. Set.
Oh, set.
Set.
Okay.
So how do you think?
No.
No? Right. Set doesn't have an order. Set doesn't have order. But list does have an order. Does have order. Okay. So that's some mathematic concepts there. Alright. Alright, so list. Alright. First it has a feature that if it has an order, then we have those index. Right, index. And then we have well, it's like array, right? We have like similar items which organized by the index, right? And then what else do you think a list should have?
complexity.
Size. Like size
Size?
or not?
Well,
Type.
yeah, you can have choose from. Yeah, it's different. Have static list, maybe dynamic list. So if it's dynamic, then we don't worry about size.
Yeah.
Even for array, array has
size, but the size grows. You know what?
yeah. But that's to the implementation level. It has a size, but size grows, right? That's you don't know. If you are implementing that, you know that. But for maybe somebody's using that, you don't want they know that detail because that's too much for them. Okay. So size, we can decide if it has size or not, right? Okay. So so that's basically how we describe that list, right? We index items and maybe have a size or not. Yeah, something like that. Okay, so if you want to do some operations to the list, what's the operation? Okay, let me write it.
Insert.
List. Okay, definition, something like that. So the element, what are the elements? Like identical typed elements, right? Typed, okay. Identical typed, indexed, right? Yeah, kind of simply describe their relations and elements. And operations.
Insert.
Yes, insert. For sure, we should have insert. And what do you think? When we insert, what do we do?
You have to figure out where you want to insert. You want to insert the
What do we give? No, not like the algorithm. What do we do? Parameters. What do we give?
Give it an
Whatever
item,
the-
an item, the item that we
Yeah.
insert.
So item, let's see, item X. And something else or just X?
you get where you want to put it in.
Like where do you want to put that item? Right? It's not like stack, we just put it on top, right? Push is on top. We don't care how much is down there, right? But list, no. What do you
You
do?
have to give the index.
Yes. Yes. Right. And the index, maybe the I, okay. And what else?
Remove.
Well, if we insert, then we should be able to delete items from the list.
Yes, then something like remove, right? And what do we give?
Whatever our value is that we're
If
trying
we
to
give
remove.
the index of the location over here,
How about value?
uh,
Do we need value?
Yeah,
Yeah.
value. We
No, there should be a search function.
Right, that's different, right? We just need the index. Delete the third item. We don't care what is there, right? Sometime, yeah. Okay. How about like let's see if we want to just delete that student name. I don't know what is the number of that student. I just want to delete, remove.
It should be a search operation, return the position, and then it has to remove.
Yes. Yes, exactly. We need to have a find. Maybe search.
Well, it's because that's a search built in. You could have like multiple versions.
Yeah, search. If you give the and what if we want to know that like who is like the ice element, then it's kind of find, right? Sorry, should be I. So this will return the number. This will return the index number. This will return the this will return the number. This will return the object, yeah, value. Yes. Yeah. Other than that, if we a list, we want to look at the list. So print, probably print that list. Okay, something like that. All right. So yeah, I'm not going into describe what is in there. Okay, just look at these operations. All right. Do we have a we do have a list. Let's assume that we do not have a list available. Okay, maybe in Java we do not have a list, or array list, those things. Okay, I know there's something there, but let's assume they do not exist. Okay, we only have some basic stuff there, like array. Okay, then we want to implement this list, these operations of the list, right? So assume if we want to use an array to implement the list, like insert. Okay. Yes. Okay. Insert. So array has the feature that we predefine the size, right? So it's continuous space in your memory. Okay. So it looks like this. So when we decide to initialize an array, it's a continuous space in your memory. So it looks something like this in your memory, and within that space it's all those elements, right? Dot 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 dot. Okay, something like this. All right, so that's an array, but the problem is the size is fixed. Let's assume we want to implement a dynamic list with this array. Let's think about insert method there. Yes, let's think about insert. Assume we already have a list of this 1, 2, 3, 4, 5 elements. Okay, we already have something there, something here and here and here. Okay, now we want to insert something over here. Then how can we do that? Assume this list is implemented with an array. Okay, now we already have a list. It's initialized with a continuous space in your memory. So basically this is an array, but we access it as a list. Okay, now since it's continuous space, now we want to kind of break it and put something in there.
Yes, we have to shift all the elements.
Yeah, you shift all the elements. Yes, okay. But problem is that's a memory, right? You do not know if there's something after it, or maybe it's already occupied before it.
You have to copy.
Yes, exactly. You need to find a new space. You need to find a new space. You cannot just put something in there, squeeze in, okay? It's not like that. It's a computer. Okay, it's not flexible. Okay. Now that's a problem. So when we do insert, we need to take everything from here. Okay, and we assign a new space. We find a new place to assign some new space in the memory. Now we have 5. Now we're going to create an array with a size 6. Then we copy the first, the second, and then we put the third, which is whatever we want to insert, and then the last 3 of them, okay, into a new space. Yeah. Let's do this. Okay. Okay. So what we do is there's a new place. 1, 2, 3, 4, 5, 6. Okay, that's 7. Alright, what we just need to do this. That's crazy. We need this. And the third one we put it here. A fourth one. So then we will have this new list insert. We implement this way, okay? So in terms of the runtime, you know what is runtime, right? Time complexity of an algorithm. So this is algorithm, right? We copy it from the old place, put it into the new space, right? So what is the runtime of this algorithm?
Like O of n. O of n.
Yes, exactly, O of n. Anyone do not understand why it's O of n? Yeah, if you do not understand, let me explain that a little bit. Because basically, O(n) means you basically need to go over this whole list and do the work for n. It's not like n squared. Okay, we have O(n), we have O(n) squared, something like that. For example, if you have a 4, maybe it's if n squared kind of 16, something like that. But the number is n. No matter it's 2n, 3n, 4n, but it's n. Okay, if we go through it once, twice, 3 times, it's still n. Okay, because the number is there. Okay, so that means it's O(n). Okay, that's cool. And then let's think about another thing, the remove. Remove. Okay, let's come back here. Let's assume we already have, okay, this 6 elements here. If we want to remove one element,
We go directly to that index where the element is located. Because we are using the index to locate the element that we want to.
Or you can just shift the elements and just leave an empty space on the end. Or you have like repeat value. You don't necessarily have to delete anything. You're
Yes.
just not using it.
yes.
So that way
Yes.
it can be like a constant.
Yeah, that'd be a good way to manage your memory, right? So you delete that thing, you just need to shift it back. For the elements that after the element you want to delete, you just shift it to the left, 1 space. Right, so what's the runtime? What's the runtime? Yeah, it's still n, O(n). Right, it's still O(n). Because basically, no matter if you You know, it depends. The best thing is if you delete the last one, it's only one operation. But if you delete the first one, you kind of need to shift everything in the loop. So on average, it should be half of the number, right? So it's still n, like 0.5 n, still n, okay? So that's n, O(n). Runtime is O(n). All right. And
so often because we are shifting, is that why?
yes, because we're shifting.
Because if it is an array implementation, we are looking at removing the element from it. It doesn't matter which index that you are.
Right, it doesn't matter.
Moving, so it's more,
Okay.
it's like
When
a
we-
constant operation, right?
Yeah.
You know, I'm thinking like it should be at row 1.
Yeah, the best case is O(1). But when we talk about runtime, we always talk about, most of the time we talk about average, right? So on average, it should be half of the n, right? So it's O(n).
Is it because we after we remove we have to shift? Is that why? That's why it's open.
I
Oh.
think what you're thinking is you're just thinking we set the value to like null or something,
You
but
don't
then you
need
end up
to-
having
you
a
don't-
gap.
you don't need
But you have to
to-
use a for loop to shift everything. Anytime you use a for loop, it's
See,
not
we
only.
are dealing with memory here, and when you remove an item from the memory, you still have the memory right there.
Yeah. If
So you can override
no,
it.
you're talking about like I just remove this, and then I just leave it blank.
Yeah.
You thinking about that? Okay, yeah, that's another different. That's not an array. That's another way that we're trying to talk. We're talking about array here. We use array, right? Because if you want, you still use the index to access those elements. You need to let them to be consistent. Okay, but if we use some other implementation, things will change. But now it's still n. Okay, O(n). It's not just remove that value. Okay.
Like if you're using a linked list, you can make it constant, but with an array, it's going to be linked.
Linked list cannot be
Yeah.
done.
So
It
remove.
depends on where you're
So
removing.
insert
If you're
is
removing from the
O(n).
head, it's constant. And if you're removing from
Because
the
all you're
head,
doing is resetting where your links are. So you don't have to go through. You can just say this link comes to there.
but if you are removing from the tail, you have to traverse the whole list. And that's all fair.
Unless if you know where the position is already.
You don't just arrive at that position, you still have to traverse the list from the head, right?
yeah, you need to traverse the list. You mean linked list?
Yes.
Yeah, I'm going to talk about linked list in a while. Don't
worry about
yeah, don't worry.
One thing
Yeah.
about the head then.
So this is O(n) as well. Search, so it's because they go through that, right, and search for it. So search is O(n), right? Okay, find I. Yes, it's 1. Why? Why is it just 1? Yeah, okay. Yeah, you already get index. So you don't need to traverse this whole array, like from 1 to 2 to 3 to 4. Because all of them have the similar space, not similar, same space. If it's 1 byte, 1 byte, 1 byte, 1 byte. So you can easily calculate the address of this cell using the index, like within the computer, okay? You can easily calculate. So you can just access this cell with its address, okay? So that's O(1). That's O(1). And print list, you have to go through everything. O(n). Okay, so that's we implement.
We need more functions, don't we? We need just to add and all that.
Yeah, that's okay. I'm just giving an example. You can have more, a lot more functions, but just as a key.
Can't you cache the list so it's constant?
Cache, yeah,
Just store the value.
yeah. Okay, so that's some special case, right? So if you're talking about special case, we can do a lot more, right? But it's just in general, right? Let's talk about implementation with linked list. Let's see is there any difference, okay? Right, we have a list ADT. The point here is we have an ADT, but we can have different implementation to one ADT. Like we have that refrigerator ADT, but we can have a lot more different implementation. Like how do we select the ice dispenser? Should we select expensive one or expensive, in this case expensive algorithm but reliable, or should we just select some? We don't care about the efficiency, but we just care about the cost, something like that. So we kind of need to evaluate that. But now here it's different for implementation with linked list. Okay, so what does a linked list look like?
Linked list has nodes with data and address.
Data and their address. So linked list is still a space, right? Okay, a space in the memory. But that's different. It's not continuous. Okay, we have a space here. We have space there.
Yeah.
We have space here. Okay, somehow, yeah, something like that. Okay, something like that. And we have a single linked list and maybe double linked list. Okay, so let's see. But kind of different is we have a pointer that link from one cell to another. From one cell to another. I need to get something I can just draw with my hand, right? That's more convenient. Okay, so and how about for array in each cell we just have a data, right? But how about the linked list? Is there any difference in one cell?
You have data and address to the list.
Right,
No.
correct. So there are actually two parts. One is the data here. We have a data here. Data here, and then we have this address, which is like a pointer, something. Like tell you what is address of the next element. Okay, so they are similar for those cells. Okay, if we're using this linked list to implement that list, it make more sense, right? Because they are lists. So let's think about insert. So what do we do in insert?
Well, it depends on where we are inserting.
Yes, it depends, but let's think about average case. In average,
So we have to find the location.
It will be O(n) then, if we are looking at the average case, it will be O(n).
yes, because when you're doing insert, um, well, it's kind of tricky because if you think about the insert, if we think that we're finding the address is actually not, it's not like getting the data. Okay, if we assume that we're finding the address, this process only counts one constant, constant time. Okay, because it's like I point to this address, point that address, so point to different address.
Again, we are finding the address, we have to go through the list if we're looking at average case.
Yeah, you're not actually access that list. You're not like fetch those data at all. You're not touching those data at all. You just went through that address, go from one to another. So assume this is like constant time. Assume this address is a constant time. Okay, then basically insert. We say it's actually constant runtime. It's 01 because we just need to put that list there. Like, for example, if we want insert a cell here between the second and third, okay, what we need to do is basically we break this connection, right? We break this connection and we make the second element, the address of next element, point to the new cell, and then we change the new cell pointer to the last cell. Okay, so it's kind of constant. So it's 01. So this is what we do. We change. And then we remove this. Okay, we break it. That's the insert.
Then how do we get to that cell, that node right there before, you know, the point where we want to insert? How do we get there?
How do we get here?
We're talking about this one. This is the new
New
node.
cell. Yeah, this is a new cell.
Insert. And how do we get to the previous node?
Previous node?
Yes. Because what I'm saying, what I'm trying to say that before we get to there, we have to start from the head. So we are in essence traversing
I
up to that point.
understand your question. Yeah. So when you implement that, when you find that element, you kind of need to remember the address of the cell before this element. Okay. So that's the implementation. I can do implementation. So it's like when you are trying to find this location, you need to go through here, 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 right? When you are reaching here, okay, you always keep 2 pointers. Okay, so 2 pointers to shift from the first 2 and then 1, 2, then become 2, 3, 3, 4. Kind of shift 2 of them together, and then if the last one find the element, then you know what is the one before it, right?
But you still have to go through all of them.
That's what I'm
right?
saying. You know, that's my point. We are traversing the list in order to get there, because we usually aren't we starting from the end?
Yeah. So usually, those address finding, those things, they do not actually count as an operation, because an operation is something like a solid operation. You're doing something. You're doing something there. So this kind of traverse, well, we just don't think that's cost. Yeah. Maybe if it's too long or yeah. You could have something there, some cost there, but compared with, okay, I'm doing something to the cell, delete, like break it. Compared with that, we think that's nothing. Okay. Yes. Yeah. Okay, let's just assume it's nothing. Yeah.
I'm more concerned with the time complexity here, on the average case, because we're not going to be dealing with just few nodes.
Okay, so if you're going to like go through it and check what is inside the cell and match if that is something we want to find, then it's probably an operation. But if you just search from one to another, we just think that's one operation, maybe just one-time operation. Yeah, it's not like a dramatically increase with the size of your array. Yeah, but if you think of infinity, yes, infinity. Yeah.
Are you saying that any searching algorithm
No,
have
no.
the big orientation of 1, or are you saying
No.
that it's only
No.
when we're inserting an element in a linked list where we're that
No.
it becomes-
It's not correct. So search, it's a lot of search algorithms, right? You
Right.
remember, right? Like binary search. Okay, so that's like log n.
So you're basically saying that because it's a linked list, we don't have to search for the elements?
No, you do not do the search. You do not touch the data at all. You just go into this pointer.
Right.
The pointer points you to another thing.
Mm-hmm. So
Okay.
you don't have to like for an array, you have to actually go and check each element. But for a linked list, you just follow the.
Yeah, it's confusing. You do have to like touch each of the pointers, but touch those pointers, it's very minor operation, actually. So
So you won't use like an external pointer that kind of traverses through the linked list. You'll just use the pointers that's already there.
Are you saying like a precondition is we already know what the previous pointer is, and so we're giving it that previous pointer as well?
no. You here. Okay. So when you're trying to find the third element, okay, you first you kind of get the entry of this list, linked list. So you reach here, and then from here you reach here, you reach this part, you reach this part. Okay. So when we want to insert this part, we do not touch this data and the data, any data before it and any data after it. Okay.
You're just going with
So
axes.
yeah, we consider that as a constant. Okay. However, what different is like define, search, find. Different. They are different. Okay. We have search operation. We have a find operation. Okay. Search in the array is n, O of n. Find in the array is O of 1 because we just need to calculate the address once and then we directly go there. Okay. But here, remove is what's that? Remove is 1. Yeah. Insert is 1. And similarly, remove is 1. And search, it becomes quite different.
And because we are taking the data and comparing.
Yeah, let me tell you, this is n. This is true n. Why?
Because we have to check the data.
Exactly, we have to check. We have to check if the data. Yeah, we have to check if the data inside that cell is something we want. Okay, it's something we want. Okay. All right. So that becomes n. Right. and print list and find. It's kind of n. Oh yeah. In this case, find should be 1. Yep. And O print list is O n, right? Because you finally have to go through everything.
What are we using to find in that case, since we don't have an index?
Again, because we are traversing with the address for that.
And then you return the value of the i's. You return the value of the i.
I would not have I. What is I? What does I represent?
I is the index. Like we want to find the second element of this list.
We don't have index in the linked list.
We don't have index in the linked list, but we have index in the list. We are using linked list to implement that list. Okay, when you are using the list, you do not know what is inside. It can be linked list. It can be double linked list, single linked list. It can be just an array. So what I'm talking about is kind of different implementation, have different like influence on that ADT. But when you talk about ADT, you only talk about functionalities, those elements and their elements and their relations, right? If you remember what we talk here, identical type for typed, and it has index. Okay, so I is index. This find I is an operation of list. It's not linked list. Okay, it's not linked list. Yeah. So that's kind of, we are using linked list to implement that list. We can also use maybe double linked list, right? If it's double linked list, it's easier to understand how can you find the previous cell, right? Sometimes, yeah, how to understand this runtime thing. Okay, so well, it's you need to first understand what is the main operation of this method. Like here, search X. Now remove and insert. Right? Okay. The main operation of insert is actually the insert itself, like break it, relink them. That's the operation of insert. That's the main thing. Okay. And then yes, we do have to go through each one of them. Okay, but that's just the address access. So compared with that main operation there, that address access, basically it does cost time, but it's nothing. Okay, it's nothing comparable with that big thing. Okay, so does this find. Okay, no, not find. Remove. It's like we need to break two links and create a new link, right? And maybe we wipe the data in the memory. So that, if you look deep into the assembly language, that's a whole bunch of operations, commands there. But those address access is just one thing there. So it does cost, but it's not cost as much as the main operation. So when you talk about it, you talk about the main operation, right? Otherwise, if you consider that as a part of the time complexity, it's going to be hard. some excellent algorithm will have a like similar algorithm like other not so good algorithm.
So
that's-
what you're saying is that it doesn't matter where we are removing the item from the list, it's still O of 1. If we remove from the head, it's O of 1. If you remove from the tail, it's still O of 1.
yes.
Okay.
Yes. Okay, because the main operation is O1. We just remove once. Okay, the main operation is remove, not go through. Yeah, we do go through that n times, but
Yeah, but going through the list still adds to the time complexity.
okay.
So that's
Let's think about this. Let's think about this. Okay, let's think about this. So we have this first level here. We have a whole bunch of classrooms, right? So that, like think about the taking class, this method, this operation. Okay, first you need to search for the class, right? You need to go through each of the door, see what is the number there. And then maybe that's only 1 second, you know, okay, maybe it's a 0.1 second, you know this is not my class. Then you come in here, you take more than an hour class, where you think this time complexity is n or 1. It's 1, just that 1. It's not like 1 hour, it's like the main operation is you are taking the class here. You spend 75 minutes here. That's the main cost. That's the main cost, okay? And when you search for those classroom, it's just maybe 0.5 second. Compared with this operation, it's nothing. So you shouldn't count that in. However, a different case is taking classes. You need to go into that class and take that class. And you come out, okay, you know, okay, I'm going there, I'm taking that class, and I know, okay, this is, okay, after half an hour, I know, okay, this is not the class I'm taking. I'm going out and going to the second classroom. I'm taking that class after half an hour, or maybe at the end of the class, I know, okay, this is not my class. I'm going out, going to another classroom. Okay, take that course, take that class, and I know, okay, it's not. Until you find this, that is the ON. Because you are repeating that main operation again, and again. Okay, given that in mind, actually, I was confused. This should be ON. This should be ON.
That's O and then the other one.
No. Think about the main operation. The main operation of find is to go through that address. Okay. So when the main operation of that method is to go through that operation, you do that n times, then this ON.
But that ON and the other ON is not comparable, right? Like the
Yeah,
previous
it's just
ON.
not, you're not comparing those two, okay?
Yeah.
So, yeah, let me give you another example. Like,
So you change the find from O1 to ON?
yes. Let me repeat that. Because when you're doing find,
But then
it's
if you're
not
removing
absolute
something,
thing.
you have
It's-
to
it's-
find it first,
yes,
right?
it's not absolute thing. Okay. So find is the main operation of find is you playing with the address. You play the address n times until you can find. Okay. But the main thing of remove, the main thing of break is the main thing of remove and insert. The main operation is insert and remove. Okay.
But for the find on the array, it's still O1, or are we changing that?
Yeah, it's still O1. It's still O1. Because in this insert, the main operation is the insert. It's not the search. Okay, like the example I just gave. You are searching for the classroom. Okay, for taking course, for taking class. If you go through that first classroom, second classroom, the tag is not my classroom. I need to find 106. Until I find 106, I'm coming here, right? I'm coming here. Wait for me. Let me finish. Until I find 106, I come here. I take that course. I only take that course once. It's constant time. Okay, that's class called take. That's a method called take class. Okay, the runtime is 01 because you only take one class. I don't care about searching for the classroom. It's not. It just can be omitted. Okay, but if you are doing a method called search for classroom, but not taking class. I just want to find where is 106. You find from the first one, second one, third one, fourth one, here. You find 106. You do that main operation n time, like n times. Then we can call it n, on. It's not like, okay, I spend 100 minutes doing this stuff. I spend only 1 minute does that stuff. That means this algorithm has a higher time complexity. No, time complexity is not measured by the absolute time. Okay, it's measured by the main operations there. Okay, so is there any question? I got it. Yeah.
Confusing.
Yeah, it is confusing. It's not like, yeah.
So where is this complexity used? Why do we use it? Where is it going to be used, the ADT's complexity? Is
It's
it
not
when you
ADT's
decide on which
complexity.
implementation?
It's. I just want to demonstrate that ADT can have different implementation, and different implementation can have different time complexity. Yes.
So now based on these two, we should go with the linked list implementation.
Well, yeah, but it still depends on a lot of other factors. But if you're thinking about, but if you like do the, if you do not do insert a lot, but you do the find a lot, probably it's a array. Yeah, it depends. It still depends, right? Yes, and like one of the method. Okay, if we are doing like similar task, O1 is better than ON. However, if we are like doing different task, like find is ON, but remove is O1, that doesn't mean remove take less time in your computer for find. Okay, find can still take less time, but it's the complexity is O1. The complexity is related to the main operation of that method. Okay, of that method. Okay, hope that's kind of clear, right? Right? Yeah, it took me a while to understand this thing. Because yeah, we do need to do this find, kind of do the find first, then do the insert. But insert has O1, find has ON. That's really confusing. But it's not like I said, it's not like we're comparing the absolute time.
Because when we're talking about find here, we're still going through the list to try to locate the item.
Yeah.
So that is why we did that. If we're going through the list, it entails traversing the list. So that is where I get lost between find and insert.
Yeah. Because in the find, it's like you repeat that operation. Maybe it's a small operation n times. Okay, you are doing a very big operation once. It's still, you take more time than you doing that small operation n times. But the time complexity, that's O1. One is still ON. You're taking one class. You're searching for n classrooms. Still O1, taking one class. Take more time. But the time complexity is O1. It's O1. Yeah, when we evaluate that algorithm, we care about the task related to it, not the actual time. We care about time complexity, not time. Okay, so it's all relative, it's not absolute. Okay, so that's really confusing. Yes.
And these like the worst case scenario time complexities.
Yeah, but we are all talking about average here. Yes. Okay, it's confusing, but I will like I'll put some implementation here. Okay, so let's try to play with a little bit of a code down to the implementation level. Like, let's try a okay. Okay, so we're trying to use kind of a linked list to implement that list. Okay, I need to let me zoom in. Can I do the zooming here?
I think if you hold control and scroll, the mouse will work.
Control and scroll. Nah. Okay, I need to figure it out. Okay. Alright, it's fine. Okay. But still, you can see that a little bit, right? If you have. Okay. I saw something. Okay, so list of cell. Okay. Now a cell, kind of like a cell in the a cell of a linked list. Okay, so it's gonna be some element like data, right? Data. So we have a, we can just say object. Object, you just call it data. Okay, and then in the linked list we also have the next data, right? Maybe the address of the next cell. So we have a cell, next cell. Okay, so here remember, in the Java we do not have a pointer, right? So pointer, what is pointer? The actual thing about pointer is it is address. Pointer is the address. So in Java we do not have pointer, but we still have address. So here in this cell address cell, here we actually store an address, a reference to its object. Okay, so that's similar to address, similar to pointer. Okay. Pointer, right? Cell, like kind of we have the next, right? Yes. Okay, then that's simply a cell. Then let's kind of have some of those functions defined. Just insert insert, we give what's that, x and I, right? So what is in insert? X and I. X is the element, right? Element. So
the type of the element we're inserting, right?
yeah, see, I do not give a type, I just give a general type object. Right. So let's just play
You
with
have to pass the
object.
So use an object here.
So it's object
Object X, and then
x. Yeah.
integer Y, integer.
Yes, integer 1. Probably we use integer for that index most of the time. Integer I. So what do we do in the insert? We remember?
Create a new cell first.
Yes, we create a new cell first. Then we find the place. We break it. And then we relink that thing. Okay. The main cost here is the relink, not the find. Let me repeat that. Not the find. Okay, because this is insert method, not find. But find is n, insert is 1. Although insert include that find. Yeah. Confusing. Alright. Insert. Okay, first we are going to create a new cell. Like cell to insert. New cell. Oh, actually, it's wrong because I haven't defined that here. Right. We have this to insert here. We create a space in the memory. We want to do this, right? So it's kind of like we have this cell here now. But the next step is going through and find the correct link. That going through doesn't take n, take 1. Alright, repeat that. Alright, I'll talk about during Wednesday's class. Okay, it's 7:46. Yeah. Alright, that's it for today. Thank you. If you still need to figure out the ON and O1 thing, yeah, please feel free to talk to me.